All right, so we're at 7.7, and now we're going to be looking at calculating equilibrium concentrations. So in this particular section, we want to make sure that you're able to identify the concentration of any of the reactants or the products in a reaction. And in order for us to do that, we're going to have to utilize a very important feature, and that is known as the Rice table. And so let's go ahead and put the Rice table here, and essentially what the Rice table stands for is for the following. So here's what they each stand for. R stands for the reaction. The one thing I will tell you here is to make sure that that reaction is balanced. So none of this is going to work if you don't have a balanced reaction. So immediately once you get the problem, you read the stem, make sure that that reaction is balanced. And then you need to figure out what the initial concentrations are. So for the most part, they're going to give you molarity for a lot of the items, especially the reactants, because those are the ones that are going to be in high concentration at 100% initially. Products are typically zero unless it's a common ion effect, but for most reactions, the initial concentration of the products is going to be zero. Now, you may need to convert from grams into moles and then divide it by the volume, but most times they're going to give you concentrations already in moles per liter. The C stands for change in concentrations, and typically remember here if you have a reaction, let me put the little drawing that I had here before, let me put it on the screen and explain. So if we have this kind of description here for the reaction, what we're looking for is the concentration over here at K. And so that means that we're going to have to come up with an expression. But remember that the change in the concentrations, notice the reactants, it's a decrease over time. And so in the previous unit lesson here, summary, I had shared if I pick 2 points in time, here and here, we could actually see that there was a reduction in the concentration this way. So going from here to the first point to the second, it was a downward reduction in concentration, so that's a negative thing. So whenever we talk about the reactants are always going to have a negative change associated with them. Keep in mind that you want to make sure that you multiply that by the coefficient because it is proportional. On the other hand, when we talk about the products, we can do the same thing here, pick 2 points for the products, and you can see that there will be a net change here. And if we extrapolate that out, you can see that the change here is also going to be from the starting point going upward, and this is a positive thing. So products are typically represented as a positive change overall. Now, how do we put this into a Rice table? Well, the last step in all of this is E, which is the equilibrium concentrations. As I just previously mentioned, when you get to the equilibrium concentrations, what you need here is a expression. So the very first thing that we're going to do here is to develop an expression. So that expression, as we had already seen, requires you then to make sure that you have some K value. And so let's go ahead and put this here like this. The K value for a very generic reaction, let me put a generic reaction up above. So here is the K expression for this generic equation. The thing is that in previous examples, we've been provided the values for a lot of these so we can calculate K, or we were provided K and maybe 3 of these items with one of them that we needed to solve for. What we're going to be doing here is we do not know what the concentrations of any of these reactants or products is, and we need to figure that out, but we figure that out at the step 4E in a reaction. So in order for us to kind of do this effectively, we're going to have to essentially do the entire steps here. We're going to have to set up a Rice table, and let's kind of do one here, but instead of just coming up with a random one here, let me go ahead and do at least one example with you and work it all the way through. All right, I'm going to go ahead and set the problem over here on the left-hand side, so let's move this over. We do have the expression value there, and so here is the problem. I'm just going to go ahead and write it up over here as an example. And so what we're going to do is we're going to take the basic equation here. Let me write it and then we'll share it. All right, so here you have the reaction above. Notice that it's not balanced. So one of the first things you always want to do with a reaction is always balance. We'll deal with that in a second. And then the problem here, for simplicity's sake, I wrote it in this manner, but you'll have a formal stem to the problem where they're going to give you everything nice typed. They'll put it in some grammatical proper English for you. But what I've just done here is I've given you some givens. We know at the beginning that we have 1 mole of nitrogen gas, 3 moles of hydrogen gas. It's going to be contained in 1 liter, and they give us a Kc value, which is the equilibrium constant value. Since the Kc value here is 1, we definitely are at equilibrium. And so what we want to be able to do is to identify here the unknown, which is the identity of the equilibrium concentrations for all of the species, which means I need to know the concentration for the nitrogen gas, the hydrogen, and the NH3. So in order for us to do all of this, first we need to make sure we balance. So let's go ahead and balance that out first, right now. And so if you look at this balancing, the balancing here right on the other side, we notice we've got 3 hydrogens on the right, 2 hydrogens over here on the left, and then we've got 2 nitrogens on the left. So initially you may be tempted to put a 2 here. And in fact, that would probably be a good idea if we do put a 2 to balance out the nitrogens. And so if we do that here, we'll get a 2 here. That will give us the 2 nitrogens we need to balance the nitrogens here. But then when you get 2 times the 3 subscript, that means we've got a total of 6 hydrogens. In order for us to alleviate it, we just simply need to put a 3 here in front of the hydrogen on the reactant side. And I'll purposely put the 1 just to make sure that there's no confusion. So here is our balanced reaction. Now we need to set up the Rice table completely. This particular step that we just did, that's actually R. So you don't need to rewrite that. But this essentially becomes the R in the process. And so at this point, what we can do is we can create a table here for I, and then create one for C, and then create one for E. Now initially, remember that the concentrations of the product is going to be 0. So this should be the easiest value that you can put. And so that'll be 0. If it helps, you might want to divide this out here so you have clear distinction as to what column belongs to what. So you don't necessarily need to put these vertical lines, but I'm going to go ahead and do that. So initially you've got that, no product. And over here for the 2 reactants, we need to use the information that was provided. So we're going to go ahead and take 1 mole divided by 1 liter. And so if I set that up here for us, the 1 mole divided by 1 liter is essentially equal to 1 molar. So I can come in here and say 1 molar. And for the hydrogen here, we're going to get 3 moles per 1 liter. So if I use a similar process, my final answer here for the concentration should be 3 molar. Now with every change that occurs, products are always going to be positive. So at the very least, I can begin by placing here minus for the reactants, positive for the products, and then the change that occurs, I'm not entirely sure what that change is, so I'm going to represent that as an X. And then I need to make sure that I consider that this change is proportional to the number of moles present, so I need to multiply it by the coefficient. So in the first column, I need to bring this 1 down and place 1 there. For the hydrogen, it has got a coefficient of 3, so I need to bring this down and place a 3 here. And then finally here for the NH3, coefficient of 2, so I need to bring this down and bring that there to the bottom, and that'll give us a 2. So these are the respective changes in concentrations, which is X, but it's multiplied by the corresponding coefficient value. Finally, what we'll do here is we're going to go ahead and add up all these items here. And so we're going to take the initial, and then we're going to add it to the change. In this case, because it is negative, it'll be plus minus X, but it does simplify to 1m minus 1x. Same thing over here, 3m minus 3x, and then finally 0 plus 2x. Now that seems a little bit too messy, so what I'm going to do is just simplify it without the m's, because we know that these are concentrations. And so one way we can do that is just take the m off and put brackets. So it'll be 1 minus 1x as a concentration here for the first compound. And then over here, this would be 3 minus 3x for the second one. And finally, this would be 2x. So now we know in this section what the concentrations are for the equilibrium. And this is actually what we want to be able to use. So now that we've got this step, we're going to go ahead and plug this into that equilibrium expression. And so that will allow us then to figure out what the concentrations are. So let me make some space here, zoom out a bit, and continue the work. All right, so I zoomed out a little bit, and here's an expression generically of what we're going to do. So we're going to take a similar approach here, but we're going to use the values in the reaction, and we're going to put that work down here. So let's go ahead and do that. So the expression here for K is going to be equal to the concentration of the NH3 raised to the second power divided by the concentration for the N2 raised to the 1 power multiplied by the concentration for the hydrogen raised to the third power. Now, at equilibrium, we could use these. Assuming we had numbers that we can just plug in, we could do that. But at equilibrium, things are different. We've already exhausted a certain amount of the reactants and we've generated some of the products. So we definitely need to use the substituted values here that we've kind of come up here at equilibrium. So instead of using an H3 as a placeholder, we're going to use the value of 2x, and we're just going to plug that in. And so what we'll do here is I'll just move this over a little bit and substitute the values here. So for NH3, I'm going to have a 2x. I'm going to raise that to the second power, and I'm going to divide it by N2. N2's value is 1 minus x. I'm going to simplify, get rid of that 1 value, so it'll be 1 minus x. Raised to the 1 power, and then we're going to multiply that by 3 minus x, or 3 minus 3x, which we'll put down here. And so this here would be 3 minus 3x, and what we're going to do here, because of the coefficient is a 3, we're going to go ahead and put the 3 outside. So we'll put that there, as so. Now the challenge for us is to figure out the concentrations, but remember we had an ability to test for significance of this change here occurring for the two reactants. What we're going to do is we're going to assume that these changes, the negative 1x and the negative 3x, we're going to assume that those portions of the equilibrium expression, which is down here, or the concentrations at equilibrium, that portion is insignificant. And so specifically what I'm referring to is this piece right here that I'm identifying in yellow. It's a highlight down here at the bottom. I'm saying that these pieces here are insignificant. And if they are, what I can do is I can just say, we're going to eliminate them from the reaction. And I'm going to simplify the overall reaction now. So moving things up a little bit, what that becomes then, if I simplify, this becomes here the 2x. We do still have to square it, but now we're going to divide it by 1 raised to the 1 power multiplied by 3 raised to the 3 power. Now the value of k was given to us, so it's important that we put that number now, and that number is 1. Okay, so let's go ahead and do that down here. We're going to rewrite everything just to make sure everything's nice and clean. So here's the rewritten portion of things, and let's go ahead and simplify both cases in the numerator and simplify in the denominator, and we'll continue to move this down so we get a nice clean calculation. So I'll just move things up a little bit, and here we go. So the value here is still equal to 1, but on the right side we're going to get the following values. So we end up with 4x squared in the numerator and then 1 times 27 in the denominator. If we keep going here, this is still 4x squared, but the bottom now is 27. So what we'll do is we're going to go ahead and calculate the 27. We'll multiply across times the 1, and if we simplify that, we're going to get 27 is equal to 4x squared. And so what you want to do at this point is you want to divide by 4 on both sides. All right, I moved it up a little bit, and here on the left side, we're going to get 6.75. And this is going to be equal to x squared. And so in order for us to alleviate the squaring, we're going to have to take the square root of everything. So we'll do here square root on the right and square root on the left. And ultimately, when we do the math here, x is going to wind up being approximately 2.6. Now that we've got the value, what we can do is we can take this value and we can put it back in. So we're going to take the value from here and plug it back in. Since we're being asked to find the concentration of all of these pieces, the concentration for the hydrogen, for the nitrogen, and the NH3, all we got to do is take these values, plug them in. So what I'll do here is I'm going to go ahead and just take a copy of all of these. So I have something to refer to, move it down a little bit, and then I'll go ahead and solve for all of these. But just so that we have all of them, the first one here is going to be the N2, this is the H2, and this is the NH3. So having said that, we come back down here. Now we've got values to report. So we're going to go ahead and do each one of these. So the first one, so the N2 concentration is equal to 1 minus 1x. We can substitute in here 1 minus 1 times 2.6 gives us a value here of the following. All right, so when we get that, we get a negative 1.6 for the N2. Now at this point, I want to clarify something. We should not be getting negative values for any of the reactants. Now, you can interpret this as, hey, we already used it up. The N2 is just being consumed. But this particular part right here, when you actually see a negative value for any of the reactants, remember that assumption that we had made? And so let me come back here. We had made this assumption right here at the very top that the change in, let me go ahead and zoom out a little bit more. We had made an assumption that the changes in the N2 concentration and in the H2 concentration, which we represented up here in the change category, we had made the assumption that that was insignificant. Based on the result of the calculation here of a negative value, that assumption that we made is not correct. And so you'll probably need to go into and do some calculations using quadratic. But this problem that I'm doing here is just for illustration purposes. So it's safe to assume that on the actual exam you won't need to do any quadratic. But I'm just showing you the mechanics of how you would solve. Once we get an x value, we can just plug into each of the values. And so let's get back into the others. And so here for the H2 concentration, we're going to have 3 minus the 3x, and the x is 2.6. And so when you do the math here, the concentration for the hydrogen gas is going to be the following. We end up with, again, with a negative 4.8. So this is just confirmation here, since our reactant values are negative values. That assumption that we made earlier on the change as negligible is not correct. But just to show the mechanics, we're just going to give you the values here. And so lastly, we need to figure out the concentration of NH3, so we'll have to take that value there. And so we'll put this over here, so the concentration of NH3 then is equal to 2 times x, in this case 2.6. And so you'll get the following. All right, so let's move this a little bit over to the left. And the value that we've got here is 5.2. So here are the 3 respective concentrations for each of the items at equilibrium. Now, if you follow the mechanics of the way we solved it here, you should still be able to answer the questions that you might encounter. This one here is just an example of a problem where the values are negative for the reactants at equilibrium, which means that this assumption that we made was incorrect. But either case, though, you can still interpret the negative sign as the reactants being consumed overall. And so that would give us, nonetheless, is still an indication of how you calculate it. So there you go. This is section 7.7.